Okay, so last time, let me remind you a bit of the last lecture. So in the last lecture, we studied this adjoint homomorphism, which is the map, which is the sort of Lie group homomorphism from any Lie group G to GL of the Lie algebra, to the Lie group of invertible matrices, invertible linear transformations of the Lie algebra, okay? And we studied properties of that. Basically, in some sense, it's some conjugation of G down to the Lie algebra level. And then we learned that the derivative, so to speak, of this adjoint map, the corresponding Lie algebra map, would be, of course, a linear map from the Lie algebra of G to the Lie algebra of GLG, which is this Lie algebra of all linear transformations on the vector space G with the usual commutator xy minus yx, the usual matrix commutator. So then the derivative, we learned that this derivative is basically just a bracket, okay? And then we talked a little bit about complexifications. And in the end, I gave the definition of the Lie algebra of a general Lie group, okay? I'm sorry, the exponential, not the Lie algebra, but the exponential map. So the exponential map of a Lie group G is just the restriction of the exponential map to the Lie algebra of the Lie group, okay? So now we have defined this Lie algebra. So let me recall the definition of the Lie algebra. So what is the Lie algebra of the group capital G? It's the set of all elements. So if you realize G inside GLMC, so to speak, then it's the set of all elements, all like in M and C, such that e to the tx is in G for all at T in R. Okay? And we saw some examples of what the Lie algebras are for some standard, like any common Lie groups. But in general, we want to know this a bit better. We want to know what exactly it is. So let's look at some examples, maybe just some simple examples to give you some geometric interpretation, and then try to actually show that this is the geometric interpretation. So let's do some very, very basic examples. So the example would be, I take G to be R, but maybe sitting inside GL2C. So then, in fact, G, there are many ways to embed this, but we can think about this as the set of matrices of the form 1, T, or maybe I should put some parameter other than T because T we have above. So 1A, 0, 1 with A in R, okay? The matrix multiplication gives the group isomorphic to R with addition, because when you multiply, these entries add up. If you multiply two matrices of this form, 1A, 0, 1, 1B, 0, 1, you end up with the matrix 1A plus B, 0, 1. So this multiplication actually turns into some addition. So you actually get R, not R cross. Okay? Yeah. Yeah, I was planning to. And so what is the issue? Let me see. I guess there was maybe I could just push this on the side and maybe do this. Okay? Hopefully this is good. Still, I don't like the fact that this border is a bit long, but anyway, so what do you see there? Yeah. That's not exactly what I wanted, so why do I see this border over here? Maybe oops. Which one should I choose? Maybe with the gallery it's easier. With the gallery it becomes better maybe. Not so much, a little bit larger, but we have side by side, we have standard. Pardon? I don't want to try that because it will just screw up things. Okay, is it good enough for today? Okay. Okay, so now what is the Lie algebra? So then the Lie algebra will be the set of, so what is the Lie algebra? It's a set of all matrices X such that e to the tx is in G. And you can see that this is matrices of the form 0, A, 0, 0 for A in R. Okay? So now, if you try to visualize this in R4, so it's kind of hard to imagine what R4 is, but let's assume that I draw the 4 axes. I mean, I just draw 3 of them and like the 4 one. So this I don't care. So the axes would be, maybe this is the X and this is the Y and this is the Z and this is the T axis. Okay. So then I have, I don't know, maybe X and Y and Z and T. So this Lie algebra will basically be this line. Okay. All right, because it's only the Y coordinate that's changing. And what about the Lie group in this picture? The Lie group will be, you know, then X and T. Or maybe I should visualize T rather than Z. Maybe this should be T. Okay. So X and T are equal to 1, and I get another line parallel to this one, right? Technically. Now, it's true that this space passes through the origin, but when we think about the tangent space to a manifold at a certain point, you can, you know, basically, if you have an embedded manifold, you know, you could say it's a subspace anyway. You don't want to think about it as an affine subspace, or you can think about it as an affine subspace. So you can, by translation, bring this space here, and you see that this Lie algebra really is the tangent line. Okay. Or if you do another example, let's take G to be S1 sitting inside C star, which is GL1C. This is maybe easier to understand. So this time I have C star, and I would like to represent this by the 2 axes, the real and the imaginary axes. And this is this group G. And now the identity element of the group is here, and the tangent line would lie here. And when you think about the Lie algebra of S1, what is the Lie algebra? So what are the elements of S1? There are things of the form e to the I theta, right? So for which complex numbers I have e to the T alpha in G? Well, clearly alpha should be an imaginary number. So that will basically be this line. In other words, the Lie algebra is an affine translation of the tangent line to the identity. Okay, so we expect the Lie algebra, so geometrically. So this intuition, and I don't want to sort of get into the technical details of the proof. I mean, I'll basically explain why it's true, like shortly with some proof. But anyway, so for the moment, so the idea, I just want to clarify the idea. The idea is that the Lie algebra is the tangent space at the identity in G. Okay, so that's what it's supposed to be. All right, from these examples we learned this, but it's not totally straightforward from what we have proven so far that that is the case. The reason is that when we think about the definition, you expect a one parameter subgroup to lie completely in your group when you have this X. And now, if you take some tangent vector, it is possible that that exponential creates a curve that's only tangent at this point, which it should be, but doesn't really lie in G. Okay. So we really need to prove that, in fact, for all tangent vectors, this happens. This e to the tx always lies in G. Okay. So for this is a little bit subtle. This is not totally trivial, and that's why there is like a couple of statements in the book related to that. So this is what we really want to prove. In other words, from our definition, it's not even clear that the Lie algebra of a given Lie group is maybe even just a zero Lie algebra. Okay, we want this to be of the same dimension as the Lie group locally. Okay, so the dimension of the vector space should be the same as the dimension of this manifold, which means the dimension of the local chart. But we need a proof. Okay, so let's try to prove this. So the proof is, as you see, it's a little bit subtle and depends on a lemma. So let me first state the theorem that justifies this. So we will justify this assertion from this theorem, but let's first state this theorem. So let G be inside GLNC, be a matrix Lie group. With Lie algebra G. Okay, so then there exists some epsilon between 0 and log 2 such that if we define u epsilon to be the set of x in M and C, such that x minus, like the Hilbert-Schmidt norm of x is less than epsilon, and if we define v epsilon to be the e to the x's with x in u epsilon, so then the following hold. The first thing is that for any x in v epsilon intersect G, the log of x belongs to the Lie algebra, and of course intersect with u epsilon, right? Maybe I should write u epsilon intersect G for consistency. And then, in fact, this correspondence is a bijection. So the X map that goes from U epsilon intersect G. Certainly, the image of this map lies in V epsilon by the definition of V epsilon, and it lies in G by the definition of the Lie algebra. But the claim is that this is a bijection. With inverse being log that goes from V epsilon intersect G to U epsilon intersect G.
It's a homeomorphism.
Yeah, it's because X is a differentiable map anyway. So when you restrict it to a submanifold, it will be locally a diffeomorphism. Not globally, but locally it will be a diffeomorphism. Yeah, I think actually it's actually globally diffeomorphism. It's true. So it's true locally, but you could just translate it. Okay, so yes, it's a diffeomorphism.
If we say bijection, it sounds like a one-to-one correspondence with dead end.
Well, we already know smoothness. So the main thing is bijectivity that we need to prove. Okay, the smoothness is really part of the fact that it's a restriction of a smooth map. Okay, to some subspace. So it's really bijectivity that we need to prove. We need to show that in fact it gives a bijection between these two the points. In fact, like a 2 is an immediate consequence of 1. If I show that the log of something in G and in this small neighborhood lies in the Lie algebra, then I am done. Okay, because I know that X is an injection onto this neighborhood. That was that was the choice of this epsilon, if you remember. So I mean, we had these facts. So maybe I should first recall some facts. So I mean, if X minus 1 Hilbert-Schmidt norm is less than 1, then log x is defined, and we know e to the log x equals x. So this means log is an injection, and similarly, if an Hilbert-Schmidt norm of x is less than 1, then, or I'm sorry, not less than 1, but less than log 2, then e to the x minus 1, well, we just noticed that its Hilbert-Schmidt norm will be less than 1. Okay, this was like part of a lemma we proved about the log function. When we studied the log function, we had this. And as a consequence, log e to the x is defined and it's equal to x. So what this means is that e to the x is an injection. With this condition, of course, right? This condition that the norm is less than log, okay? So for bijectivity, I really need some kind of surjectivity, and that surjectivity comes from the fact that anything in here is e to the log of something. So in other words, I wanted to show that log takes elements of capital G into lowercase g, the fracture G. Okay? All right, is it clear? So therefore, so from this, this means that 2 follows immediately from 1. Okay? So part 2 about the bijectivity requires some surjectivity, which is a consequence of 1. Because injectivity is there for a neighborhood less than like log 2 all the time. But we want to take epsilon less than log 2 anyway. All is good so far? So now I want to prove this part 1. Okay? So the proof of part 1, I'll postpone to after the following lemma. Okay? So we need the following lemma. So we need a technical lemma. So what is the lemma? The lemma is the following. So let Bn be a sequence. And since maybe we had n for the dimension GLNC, maybe I should use Bm. Be a sequence in G, in capital G. So a sequence of points in this Lie group, okay? Such that they converge to the identity. So these are points that are approaching the identity, okay? And now, for sufficiently large m, the log exists because they are sufficiently close so that this condition less than log 2 is met, okay? Now set ym equals log bm, so this makes sense for m sufficiently large, okay? But we only care about sufficiently large, okay? In what I want to assert, right? And now suppose that all the yms are non-zero for sufficiently large m. Okay, so now what I can do is I can normalize them. So I can consider this ym divided by norm ym. This will be now a unit vector. Okay, and now the claim is that this converges to y where for some sorry. This is not the claim. That's not the claim, of course. I can normalize them. Okay, suppose that this is 0 and we have then the sequence, the normalized sequence converges for some y in MNC. So then the claim of the lemma is that in fact this limit is in the Lie algebra. Okay, so I have this identity element and I have a sequence of points approaching, like I don't know, b1, b2, and I can write them as e to the y1, e to the y2. And I would like to normalize this ym divided by norm ym. And if they converge to something, the limit should be in the Lie algebra. That's the claim. Okay. So let me explain the proof of the lemma, and then we will use this lemma to prove the part 1. Okay, so the proof of the lemma. So how do we prove the lemma? So first, let us note that in fact the yms converge to 0. I mean, that's because like there are logs of things which are converging to the identity, and you know, basically exponent log give bijection between 0 and identity. Okay, so I mean x goes in this way to identity and log goes in this way, and neighborhoods around them are mapped back and forth. Right now, this is about like exponent log, not on G and the Lie algebra, but on the matrix space. Okay, we can also treat this more precisely. You could say that well, ym is really log bm. So this is really log of 1 plus bm minus 1. And when this becomes sufficiently small, which it does because bm converges to 1, you can write the Taylor series, the sort of the power series that describes the log. And from what we learned there, this is bm minus 1 plus something of a small magnitude in like a quadratic order. This is a consequence of looking at the Taylor series. When we talked about this convergence things, when we talked about the log series, we also learned that, okay? And of course, this goes to 0. This is all Hilbert-Schmidt norm, okay? So this goes to 0. And this also goes to 0. So this means that ym converges to 0. Okay, so now I would like to show certain element is in the Lie algebra. The only tool I have so far is the definition of the Lie algebra. So the goal is to show, so we show e to the ty belongs to G for all t in R. This is the goal. So first we noted that this yms go to 0. So now ym divided by norm ym is converging to y. I can just scale this, okay? Or more precisely, what I can do is the following. So I want to basically look at this ty as a limit, but I want to get some group elements. So what I do is I just take some integers. So choose like integers km such that km times the norm of ym converges to t as m goes to infinity. Oops. So why can we do this? Well, we know that this is a quantity that goes to 0. If I wanted a good km, what should km be? Km really, if I wanted if this is equal to t, km should be basically t divided by norm ym, right? But I want km to be an integer, so I could maybe choose this. All right? So then what happens if I choose that? Then km times norm ym, well, this quantity is between t over ym and t over ym minus 1. So this quantity km norm ym is definitely less than or equal to t, because I just have like t over ym times ym. And on the other hand, it's bigger than or equal to t over norm ym minus 1 times norm ym, which is really t minus norm ym. And of course, norm ym goes to 0. Okay, so by this choice of km, I get some integer, positive integer km, of course, for like m sufficiently large, so that km norm ym converges to t. Okay, all right, so that's really not hard. And now I look at this. I look at e to the km ym. So this I can write as e to the km norm ym, which is getting close to t, times ym divided by norm ym. Okay, right now we look at this. So this part converges to t, and this part converges to y, and the exponential is continuous. So this converges to e to the ty as m goes to infinity. Okay. On the other hand, what is this guy? This is e to the ym multiplied by itself km times. So this is e to the ym times e to the ym. These guys, they are in G, right? Because they are actually equal to bm, right? So this is like bm to the power km, okay? So this is in G. So what I have is a sequence of points converging, and they're all in G. But G is closed, so the limit should be in G, okay? Since G is closed, the limit e to the ty must be in G. So this means that y is contained in G. Okay? So we proved this kind of technical lemma. A sequence with normalized converging and coming as logs of things that go to 1 will have a limit that's in the Lie algebra. Okay? So now let's go back to the proof of part 1. So what is the statement there? The statement is that, let's go back to the theorem. If I take, so there is some epsilon sufficiently small so that any element in this small neighborhood in G has log in the Lie algebra. Okay, log being in the U epsilon is trivial by definition of V epsilon and U epsilon. I need to show it's in the Lie algebra. Okay, so the proof is by contradiction. We assume that there is a sequence not satisfying this, which means for every epsilon there is some point not satisfying this, and therefore we get a sequence going to the identity not satisfying this, and then we reach a contradiction. Okay. All right, but there's a little bit more work to do. So here's what we do. So first, so G is a subspace of M and C. And anytime you have a subspace, you can choose a complement. Okay, so choose a vector space complement. Let's call it D, i.e. M and C is a direct sum of G and D. The direct sum of these two vector spaces, okay? And now we have this map phi. That goes from M and C to M and C. Oops. I hit something really strange here. I got so many strange letters. Oh, okay, they're gone. All right. So M and C. Set this to be this map. So any element of the domain can be written as x plus y, where x is in G and y is in D. Okay? And now what you do is you just exponentiate in each part, e to the x, and you get e to the y. Okay? And then you multiply these exponentials. So I don't want to consider e to the x plus y. That will be just exponential map, but I want to consider these separate exponentials. But the thing is that this map is still a smooth map because exponentials are smooth, and it has derivative equal to identity. Its derivative is the same as the derivative of the exponential map, even though it's not the exponential map. And that's because you can do partial derivatives of this map. So note that. Oops, note that. If I differentiate this along the line Tx, okay, so this is the partial derivative along direction x, okay? So what I get, and I do this at t equal to 0, then I have the derivative of e to the tx times e to the 0, which is identity. But the derivative of e to tx will be just x, okay? And the partial derivative of this map with the other coordinate or any direction y at t equal to 0 is again y. So you see that the derivative of this map, so that the derivative will be again a linear map, so it's like d phi. So d phi, the derivative will also be a linear map, this time from M and C. So I'm doing calculus again, right? You should recall your multivariable calculus. And the claim is that this is the identity map. Okay, so we should say clearly phi is smooth. So if I have a smooth map, if I want to compute this derivative as a linear map between these big spaces, of course, the most natural thing to do would be to differentiate, like do the partial derivatives. Okay, you did all of this in your multivariable calculus, right? You wrote this matrix. How did you do this? Like df xj, like dfi over dxj. That's what I'm doing, right? All right, so now the derivative is identity. And now, if you remember from your calculus courses, we have this thing called the inverse map theorem, inverse function theorem, which says that if the derivative of a map is invertible, then it locally provides a diffeomorphism. So by the inverse function theorem, so this might have been done in the analysis courses. How many are familiar with the inverse function theorem? Nobody? You haven't taken the third year analysis? We do this third. You didn't do it? Was it assumed in the third year? I have never taught the third year analysis courses. Is it assumed that you know this? No? You did also in multivariable calculus, maybe inverse function theorem? Anyone else?
Calculus is taught as like calc 1 and calc 2. You don't really do proofs.
Yeah, we
It's
did a
like-
lot of like compilation and stuff like.
Yeah.
But then I thought that third year analysis we prove these things.
No.
No?
But it's okay. I mean, we can take your word for it.
Okay, it's calculus. So I mean, okay, you don't have to memorize this proof. I mean, you just have to trust that there's such a theorem. What is the UK system? You guys know this theorem? No? Okay. All right. It's a little bit surprising to me because it's sort of a pretty standard fact.
Multivariable calculus, but it's not immediately useful. So
Okay. So what about, maybe you know it by a different name? It has its relative. What is it called? Not the inverse function theorem, but implicit function theorem. Mahan, do you know this theorem? Means you do, or okay, hopefully this means yes. Okay, so implicit function theorem. You guys know the implicit function theorem? No? Okay, all right. Okay, so what is this theorem? The theorem, did you understand the theorem? Or maybe I will write it momentarily, but did you understand what the theorem is? Like, can you guess what the theorem is? Actually, sometimes in mathematics, it's good to kind of be able to make a good guess. You see something and say, okay, I don't have to read this book, but I can guess what is done in this theorem. This is what it should be, maybe, okay? Okay, so anyway, what is the inverse function theorem? So inverse function theorem is that if phi from Rm to Rn is differentiable. Maybe I should say, okay, just say smooth. I mean, we need C1 probably, but I don't know. Maybe it's C infinity. It's like infinity many times differentiable. And I hope that you guys know that in this case, D5 will be a linear map, right? Like this, huh? Okay. So, and if this is invertible, which of course implies m equals n, maybe I don't know, maybe I should have chosen m equals n in the beginning, then like phi restricted to U is a homeomorphism, is a diffeomorphism, maybe I could say. So it's even a homeomorphism, but of course the diffeom. From U on to phi U for sufficiently small. Maybe I should say the derivative at 0. I mean, I have to fix my point. I don't know. I can fix any point. Derivative at P. Huh? What's the diffeomorphism? Diffeomorphism means it's a bijection with inverse also differentiable map. Like a homeomorphism which is differentiable and its inverse is differentiable. Are you familiar with this theorem? Okay. All right, so now by this theorem, we know that we have some open neighborhood in around the 0, which is like surjective onto another open neighborhood. So the point is this is open. So this is open also. Okay. The most natural thing you expect, which is true, and you know, and of course, for those who took algebraic topology with me last semester, you know that it's also true technically in some form for continuous maps, but it's much harder to show. This is the invariance of domain theorem. Okay, we don't need homology for the differentiable version, but for the continuous version you do. Okay, so now what is the consequence? So choose, you know, choose U neighborhood of 0 in M and C such that ST means such that phi from U to phi U is a diffeomorphism. That means like a bijection with differentiable inverse, with C infinity inverse. Okay? So now we started with this decomposition. So let us now assume that the assertion of 1 is false. So in other words, for every epsilon, there is some x such that this log doesn't fit there. You can choose like a decreasing sequence of epsilons. Maybe I should say. So now suppose, oops, let me see, there's a question. Okay, this is an answer rather. Okay. Thank you, Ma. Okay, so now everybody's in the middle of the page. Okay, so suppose for m bigger than or equal to 1 for any integer, for all, maybe I should say for all such m, we have bm, or rather, okay, maybe I just use a different, okay, am in v 1 over m intersect g such that the log of am, which is defined because like m is sufficiently small, is not in maybe instead of this I should maybe say like better, maybe bigger than 10, whatever, to have like something less than log 2. Okay, I mean less than like 1 over m less than log 2, whatever. I think 3 would be enough, but anyway. So I want this to lie inside, I want this not to lie in G. It certainly is in U 1 over m by definition, but now let's assume it's not in G. Okay, this will be contradicting 1. Proof of contradiction. Okay, and now I want to reach a contradiction from this. Okay. So now the point is that since image of so this phi of U is open, so we can write AM as e to the xm e to the ym for xm in G and ym in D. Okay, because for sufficiently large m, this point will lie in this open set. This is an open neighborhood of 0. Okay, and these things are converging to I shouldn't say 0, maybe identity. So this is an open neighborhood of identity, like open neighborhood of the identity in G, of the identity in like GLNC, not just G. I mean like in GLNC. So then the sequence AMs will lie in this neighborhood for sufficiently large M, and therefore you can write it as like, because it's in the image of phi, it can be decomposed as such. So maybe I should say for M, I don't know, sufficiently large. Okay, is it good so far? Everybody following? what I'm doing? All right. So now what do we do with this? Well, so the claim is that the YMs are non-zero. Okay. So if YM is 0, then what happens? So then AM is e to the xm, and therefore log AM, it is just log e to the xm. But we know that xm is in some good neighborhood, right? Xm, it can come from some small neighborhood. So this log of e to the x will be just xm. So this, I could say again, this is like for m sufficiently large. Note that for m sufficiently large, because this map like is a diffeomorphism, this phi is a diffeomorphism from a neighborhood of 0 to some neighborhood of identity. As the xm's converge to identity, their preimages should converge to 0, which would be log. Okay. All right. So then, so we have this. So what is the meaning of this? The meaning is that that the log is actually in G. So hence, log AM belongs to G for m sufficiently large. And that's a contradiction. Okay? So the assumption that Ym is 0 for sufficiently large m is a contradictory assumption. So I don't have that. I know that Ym is non-zero. So this means we can now assume, hence we can assume, so, oops. Okay. We can assume that the Yms are non-zero for all m sufficiently large. Okay, but now we can use this lemma. All right. So how do we use the lemma? So what we do is now we set the BMs to be e to the minus xm AMs. So this will be just e to the ym. But note that the xm's are in the Lie algebra, so this exponential is in capital G. And these guys are also in capital G by our assumption. So as a conclusion, the e to the yms will belong to capital G. All right. So the BMs lie in capital G. And now, well, the BMs might not converge, but we know that the YMs, yeah, okay, well, okay, the BMs actually do converge, sorry, so, but it's the, so I have to choose something else. The BMs certainly converge to the identity, because anyway, the XMs are, so on, are going to 0. But I would like to consider, well, I mean, there's another condition to check. You remember that in this lemma, when we had the sequence ym, we needed to check that the normalized sequence converges. All right. And here, a priori, it might not converge. But by passing to a subsequence, we can assume that. And that's a consequence of, what do you call it? Bolzano-Weierstrass? Yeah. Okay. So the point is that, so since the unit ball of D is compact, we can assume by passing, or rather by passing to sub, no, it's okay, by passing, after passing to a subsequence, we can assume that ym divided by norm ym converges. Okay. because these are all normalized. They're not even like on the boundary of this unit ball, and that ball is compact, so it will have a convergent subsequence, right? And now, well, so if this, so now what is this limit? Okay. So suppose that y equals the limit of the ym divided by the norm ym. As m goes to infinity. So now the lemma says that this limit should be in G, right? As you see the lemma, with everything, all the conditions of the lemma are met, right? So there's the lemma. The lemma is here. The claim of the lemma was that this y is in G, right? So by the lemma, but however, ym divided by norm ym is also in D. D is a closed subspace, like it's a closed subset. So any convergent sequence should have a limit in D as well. So since D is closed, we must also have y in D, hence y would belong to G intersect D, which is 0. But that cannot be the case. Why? Why can't y be 0? That's right, because it's a limit of a sequence of norm 1 things. Norm is continuous, so the limit of the sequence will also be of norm 1. Okay? So with this trick, we managed to show that the log is a surjection from that neighborhood intersect capital G onto a small neighborhood intersect the Lie algebra. Okay? And as a so we have proved this lemma, and now we have the following corollary. It's like a qualitative statement of the same theorem. Okay, so the corollary is that let G be a matrix Lie group. And G be the Lie algebra, G, then there exist open sets, open neighborhoods. U of 0 in G and V of the identity in capital G, such that the exponential map and the log are bijections. And indeed homeomorphisms or diffeomorphisms. Okay? Is everybody happy so far? So now this does what we want, because if we know that a neighborhood of the Lie algebra and the neighborhood of the group at the identity and the 0 are like a diffeomorphic, then the tangent spaces to these things are the same. But the tangent space of the neighborhood to the Lie algebra is just itself, and the tangent space to this group is just a tangent space. So we just learned, like as a consequence, that the tangent space of at the identity of the group is just the Lie algebra. Okay. Okay, so maybe here's another corollary. I mean, this is a little bit technical for those maybe who kind of are familiar with the concept of a manifold. If you do not know manifolds well, it's okay. I mean, this course we will not really use a lot of manifold theory, so it's okay if you didn't understand this statement very profoundly. So, but the claim is that the G be a matrix Lie group. the algebra G, oops, lowercase g, a fracture. So remember, a manifold is like a topological space which has these charts. We talked about the definition, so we need these charts. So now the claim is that G becomes a submanifold of GL and C, okay? Which means that we have to provide the charts, but the exponential map and its translations will provide these charts. So let me just first give the assertion, and then I give the explanation. So G is a smooth embedded submanifold of M and C. And the second is that G is also locally path connected. So the consequence of this would be that if G is connected, then it's path connected. In other words, for Lie groups, being connected and path connected are not different. Remember, we defined a connected Lie group as a Lie group that was a path connected space. And the natural question is, why didn't we define it as a connected space? Now this answers, because being connected and path connected are the same, right? And connected in particular. Or rather, consequently, if G is connected as a topological space, it's also path connected. Every path connected space is connected. That's the easier side. The other side is not true. If path connected space doesn't have to be path connected. There are these counterexamples. Does anybody remember a counterexample? Space that's connected but not path connected. There's the standard example coming from sine of 1 over x, this kind of space. So you have this kind of, oops. It's kind of approaching here, and you take this line segment here plus this curve. Okay, it's not path connected. You cannot connect a point on this line segment to a point here, but you cannot separate them by open disjoint open sets either. Okay, is this familiar? Okay, some people have seen this example. Not so much. Okay, so it's okay. It doesn't matter. I mean, we chose path connectedness as our benchmark. So, all right. So now, what about 1? Why is this? Why is G a smooth submanifold? Well, the charts are given by the exponential map. Okay. So first, the chart at the identity is okay. Maybe so x. So U epsilon to V epsilon intersect G. Okay. Is a chart at the identity in G. Okay. So we have like, I don't know, maybe this is the identity point on G, and we have this, this is G maybe. So this is G, and this is this V epsilon, and this is the Lie algebra, and this is this U epsilon. So this exponential map gives a diffeomorphism from here and here. In particular, it's that chart there. But what about that other points? How do we get other points so that the charts, like the sort of the interaction between the charts remains smooth? We just do the translation. So for any G, we can also consider the chart map. Again, going, maybe I use like phi G, going from this U epsilon intersect G to G, where phi G of X is, excuse me, G times X of X. So translation. You just translate this chart to somewhere else on the group. I mean, if you take another point on the group, G, you can translate this whole thing here. Okay, and now you can see that the interaction between the charts are just the composition of exponential maps and their inverses, so it will just be a smooth. So you get a smooth atlas, all right? And what about the second part? This is like the locally path connectedness. The local path connectedness is a consequence of these charts, because for any point, I mean, so this is for one, and now what about two? For any point, so rather, so like any point G in G has a neighborhood homeomorphic to U epsilon intersect G, which is connected, which is path connected. It's some open subset. You can choose the subset to be connected. You have a subspace, you have some open set that you can take the connected subset there that is homeomorphic to some open set around G in the group G. Okay, is it clear? No?
Because I thought we did the
Well, by these translations, you can go to any point. Okay, so this translation is a homeomorphism between this open state and connected subset of G, which is like some vector space, to some open subset in G.
not necessarily differential.
Well, it is differentiable because the group operation on G is smooth, and this is the composition of translation and exponentials. It's a smooth and composition of smooth things. Yeah. Okay. So now here is another corollary. Maybe this is sort of formally stating that tangent spaces are the same, but just we can think about the tangent space also. Okay, how do you define the tangent space of a manifold? There are many ways, but you can also think about it as follows. You take all the curves that pass through that point and take the tangent vectors of the curves at that point. So these tangent vectors for different curves, they span some subspace of the ambient space. And that you want to call the tangent space. That's another definition. And from what we did right now, we can show that the tangent space defined that way is the same as the Lie algebra again. Okay, so that's the assertion of the next corollary. Okay, so let G be in GLNC be a matrix Lie group. And let G, be the Lie algebra of G. So now for any X in MNC, we have the following, maybe I should say the following are equivalent. So the first is that X is in the Lie algebra, which means like e to the Tx is always in G. And the second is that there exists a C infinity curve, like a gamma going from -1, 1 to G, to MNC. Maybe I should say MNC first. Such that gamma of T is in G for all T. Gamma of 0 is 1. And the derivative of gamma at t equal to 0 is x. Okay, so the second one would be this tangent vector to a smooth curve on the surface on G. Okay, so this is the sort of typical definition of a tangent space, one of the typical definitions. Whereas this one is not exactly the definition of a tangent space. Again, by the same issue I explained before, because the curve, a curve passing through here might not be an exponential. Okay, so we have to show that if you have a vector obtained as such, it is really the exponential e to the tx will also lie in G. That's what you have to show. But now what we showed, we have what the things that we have showed, it's now fairly straightforward to verify this. So how do we verify? First of all, 1 to 2 is trivial. This is the trivial direction. As we can take gamma t to be to the tx. Okay. 2 to 1 is non-trivial. So let's like, I mean, it's not, it's less trivial, let's say. So 2 to 1. So given such gamma, so we can write, so suppose x from v epsilon intersect, or rather u epsilon. Maybe I should, suppose, given such gamma, and maybe I should write and an epsilon positive such that x going from u epsilon intersect g to v epsilon intersect g is a diffeomorphism, in particular is a bijection. So what we can do, we can set gamma, gamma of t for t near 0 will have image in here. Therefore, it can be written as the image of the exponential, maybe some delta. For delta t in u epsilon intersect g, whenever t is small, whenever t is sufficiently small. Okay, because for t sufficiently small, the value of gamma t will lie in here, so it's in the image of the exponential. Okay, so now the gamma of t is now e to the delta t. What was the goal? The goal was to show that the tangent vector at 0 was in the Lie algebra. So let us differentiate this again. So now d dt gamma at t equal to 0. I don't know. I mean, based on my previous convention, maybe I should write at t equal to 0 here. So what is this? This is, we're looking at this formula. This will be delta prime 0 e to the delta 0. But delta 0 is identity, so this is just delta prime 0. But delta has image only in the subspace. Remember, we talked about it. If you have a curve with values in a subspace, its derivative will also lie in that subspace. Okay? So after this technical work, we know that this Lie algebra is a good thing. I mean, it's like it has the tangent space, it has the same dimension as the Lie group, and so on. The exponential map gives a local diffeomorphism between a neighborhood of 0 in the Lie algebra and a neighborhood of identity in the group. This is the most important fact. Okay, this local diffeomorphism. The exponential map, as we know, it might not even be surjective in general. So we cannot hope that it provides a diffeomorphism from the Lie algebra onto the whole group. But at least locally, it provides a diffeomorphism in the neighborhood of 0 in the Lie algebra onto a neighborhood of identity in G. Okay? So this is the takeaway message, so to speak. How much time we have? Okay, we have a little bit more time, all right?
We have delta prime at zeros in G, but we don't have that at x. It's that important.
Well, what do you mean? I mean, this was the definition of x. X was the derivative of gamma. Okay, this was the assumption. So I want to show that this derivative of gamma at 0 is in G. Okay, thanks for asking. I mean, the proofs can sometimes be kind of too long to forget what the assumptions and the conclusions are. Okay. Okay, so now here's another problem. Let's move away from this a little bit, but use all of these tools. So this is another useful statement. So let G be a connected. Remember, connected and path connected are the same. So connected means path connected. Be a connected matrix T group.
I don't think we see it.
Why did I pause it mistakenly? Why don't we see this? Did it freeze? What happened? We close it and then share again. Oops. Something in the chat. Okay, not here. Okay. Just open it one more time. Okay. But it's not updating here. Why? I'm sharing it, so let me see. That's bizarre. Did it crash here? Oh, Zoom is not responding. What should we do? Okay, well, we have to close. We have no choice. Hopefully, we will not lose Mahan. Stay in. Okay, so it seems, did we lose Mahan? Okay. And what about sound? Okay, sounds good. All right, perfect. Pardon? Yes, your screen I turned off. Okay, now you guys can see it too. All right. Okay, so what's the assertion? The next corollary. So the assertion is that, well, the exponential map is not surjective, as we know, but at least every element can be written as product of exponentials. This is the useful consequence. Okay, so this is the assertion. So let G be a connected matrix Lie group. Then every element of G can be written as e to the x1 up to e to the xn, maybe m, because n is always like GLN C, for some x1 to xm in the Lie algebra. Okay, so every element can be written as a product of exponentials, at least, in a connected Lie group. Okay, so well, we have about 5 more minutes. So, okay, let's finish the proof of this assertion. By the way, I forgot to mention at the beginning of the class that the second assignment is posted. Have you guys received any confirmation that you have the second assignment?
No confirmation.
Okay, so basically Moodle doesn't send any notification when I upload something. Okay, but anyway, Mahan, did you see this first second assignment? Not yet? You guys saw it? Pardon? Hopefully in the next few days. I'll try to grade in the next few days. Okay, so it is posted, Mahan. It's posted on Moodle. You should be able to see it. I just want to know if you got a notification, because the system at Ottawa sends notifications, but maybe Moodle doesn't. But anyway, so the second assignment is there now, and I will hopefully grade this first assignment very soon. All right. So, okay, how do we prove this assertion that every element can be written as a product of exponentials? So the idea is the following. There are many ways to prove this assertion, but here is one way. So you take the identity element and you take any element G. Okay? You want to prove that this G is a product of exponentials. So let's first connect them by a path because we're assuming G is connected. So we really have to use path connectedness somehow. All right. So now, well, we know that there is some open neighborhood of G, which is in the exponentials, right? They are exponentials. They're like in there because X is a diffeomorphism on this neighborhood. Okay. Therefore, for some small t, at least we know that the interval from 0 to t on this path is in the image of exponential. Okay, but how do we continue? Well, the point is that if you want to continue this path, so suppose this is like a point t1 and you have another point t2. How do you try to write this gamma of like a gamma of t2 as the image of the product of exponentials? Well, if gamma of t1, gamma of t2 inverse, or maybe if I write gamma of t1, yeah, if this is a small, if this minus identity is a small, so maybe I just so idea for the moment. If this is a small, so then what do we have? Actually, maybe I should say if gamma of t2, gamma of t1 inverse. So that would be better. Okay, t2, t1 inverse. So then gamma of t2, gamma of t1 inverse should lie in the image of the exponential map. It should be e to the sum x2. But then gamma of t1, we know it's e to the sum x1. Hence, gamma of t2 equals e to the x2, e to the x1, for example. Okay? So if I can show that I can find a sequence of points such that the ratios, so to speak, this like gamma of ti plus 1, gamma of ti inverse, if these ratios have are within a small distance of the identity, then all of these ratios are exponentials, and therefore the last one, you have this telescopic product. You can just, you could use relations like this successively to express gamma of G. I'm sorry, gamma of 1, which is G. So this is gamma. So gamma of 1 is G. The element G, it's not the Lie algebra, it's the element. We can use this to express this element as a product of exponentials. Okay, so that's the idea. But what is the technique to guarantee that you can find finitely many points such that these ratios are small? Does it remind you of anything in analysis?
It's a compact set. Somehow.
Yes, you're very close. So what property of a compact set should we use now?
Because the target is continuous, you probably should get that around the path or something.
That's right. And so then this actually has been formalized. You have a continuous map on a compact set, then what do you know about it? Yeah, but then the continuity becomes stronger. What do we know? Uniform continuity, exactly. How many people are familiar with uniform continuity? You're familiar with uniform continuity? Good. You guys are familiar? You guys, okay. And you're familiar with uniform continuity? No? Okay, so I will state it here anyway. So, Mohan, you're familiar with uniform continuity? Yes, good. Huh? Okay. All right. But now, since we're kind of running out of time, maybe I just okay. So I will complete this proof. So we use uniform continuity. I'll explain this next time, which will be on Monday. Okay, so we move forward by talking about representations of Lie groups and Lie algebras. And then we will also have a thorough look at representations of SU2, which is a fundamental thing in Lie algebra, Lie group theory. That will come next week. But for the moment, I guess we can stop right now. Any questions?